All right, we're on problem number 7, and when I copied and pasted, I made it a little bit smaller, so I'm going to read it for you just in case this is too small for you to read. But it says, use the proof to answer the question below. So they gave us that angle 2 is congruent to angle 3. So angle 2, or the measure of angle 2, is equal to the measure of angle 3. I'm starting to get the knack of the language that they use in geometry class, which I will admit, that language kind of tends to disappear as you leave your geometry class. But since we're in geometry class, we'll use that language. So the angle 2 is congruent to angle 3, which means that their measure is the same, or that they're the same angle essentially. Fair enough. So let's see. Statement 1, angle 2 is congruent to angle 3. That's given. I drew that already up here. Statement 2, angle 1 is congruent to angle 2. Angle 3 is congruent to angle 4. So they're saying that angle 2 is congruent to angle 1, or angle 1 is congruent to angle 2. That's there, right there. And that angle 4 is congruent to angle 3. Fair enough. And they say, what's the reason that you could give? And I don't know what I forgot the actual terminology, but in my head I was thinking, oh, opposite angles are equal, or the measures are equal, or they're congruent, right? And you could just imagine two sticks and change the angles at the intersection. You'll see that opposite angles are always going to be congruent. But let's see, that is the reason I would give. Opposite angles are congruent. Let's see which statement of the choices is most like what I just said. Complements of congruent angles are congruent. Complements. Vertical angles are congruent. I think that's what they call opposite angles. Vertical angles. I think that's what they mean by opposite angles. Supplements of congruent angles are congruent. That's not true. Corresponding angles are congruent. These aren't corresponding. I think this is what they mean by vertical angles. Complements of congruent angles are congruent. You know what? I'm going to look this up with you on Wikipedia. Let me see. Vertical angles. As you can see at the age of 32, some of the terminology starts to escape you. What matters is that you understand the intuition, and then you can do these Wikipedia search to just make sure that you remember the right terminology. Let's see what Wikipedia has to say about it. Vertical angles. A pair of angles is said to be vertical or opposite. Oh, I guess I used the British English. Opposite angles if the angles share the same vertex and are bounded by the same pair of lines, but are opposite to each other. Right, so somehow, growing up in Louisiana, I somehow picked up the British English version of it, maybe because the word opposite made a lot more sense to me than the word vertical. With that said, they're the same thing. Wikipedia has shown us the light. And so my logic of opposite angles, is the same as their logic of vertical angles are congruent. Next problem. Next problem. I'll start using the US terminology, although I think there are a good number of people outside of the US who watch these, so maybe it's good that I somehow picked up the British English version of it. Okay. Once again, might be hard for you to read. I'll read it out for you. Two lines in a plane always intersect in exactly one point. Fair enough. Which of the following best describes a counterexample to the assertion above? So I like to think of the answer even before seeing the choices. So can I think of two lines in a plane that always intersect in exactly one point? Well, what if they're parallel, right? What if, I have, let me see, that line and that line. They're never going to intersect with each other. They're parallel. That's the definition of parallel lines. The other example I can think of is if they're the same line. I mean, I guess you might not want to call them two lines then, but I would. If I had this line and then I had another, well, that's parallel, but imagine if they're right on top of each other. They would intersect everywhere. So either of those would be counterexamples to the idea that two lines in a plane always intersect in exactly one point. And if we look at their choices, well, okay, they have the first thing I just wrote there. Parallel lines, obviously, they're two lines in a plane, but they don't intersect in one point. Problem 8. I'm going to make it write a little bigger from now on just so you can read it. Okay, this is problem 9. Problem 9. Which figure can serve as a counterexample to the conjecture below? If one pair of opposite sides of a quadrilateral is parallel, then the quadrilateral is a parallelogram. So once again, a lot of terminology, and I do remember these from my geometry days. Quadrilateral means four sides, right? A four-sided figure. And a parallelogram means that all of the opposite sides are parallel. So for example, this is a parallelogram. I don't know if you remember, well, you know, this, let me see if I can, how well I can do this. And then like, well, that's, if you ignore this little part that's hanging off there, that's a parallelogram. And if all the sides were the same, it's a rhombus and all of that. But that's a parallelogram, and that's parallel because, that's a parallelogram because this side is parallel to that side, and this side is parallel to that side. All the sides are parallel. Now they say if one pair of opposite sides of a quadrilateral is parallel, then the quadrilateral is a parallelogram. So I want to give a counter example. So let me draw a figure that has two sides that are parallel. So let's say that side and that side are parallel. And then I don't want the other two to be parallel. Then it wouldn't be a parallelogram. And let's say the other sides are not parallel. So they look like, let's say they look like that and like that. And once again, that, you know, just digging in my head of definitions of shapes, that looks like a trapezoid to me. So let's see. Yeah, good. You have a trapezoid as a choice. Trapezoid. All the rest are parallelograms, right? A rectangle is all the sides are parallel, and we have all 90-degree angles, right? Rectangles are actually a subset of parallelograms. Rhombus are, we have a parallelogram where all of the sides are the same length. All the angles aren't necessarily equal. Square is all the sides are parallel, equal, and all the angles are 90 degrees. So all of these are subsets of parallelograms. This is not a parallelogram, although it does have two sides that are parallel. So this is the counterexample to the conjecture. I think you're already seeing the pattern. A lot of geometry, the terminology is often the hard part. The ideas aren't as deep as the terminology might suggest. Okay. Given trap, that already makes me worried. All right. Given trap is an isosceles trapezoid with diagonals RP and TA, which of the following must be true? An isosceles okay, let's see what we can do here. So an isosceles trapezoid means that the two sides the two kind of sides that lead up from the base to the top side are equal, kind of like an isosceles triangle. So let me draw that. Actually, I'm kind of guessing that. I haven't seen the definition of an isosceles triangle anytime in the recent past, but an isosceles trapezoid, but it sounds right, so I'll go with it. And that's a good skill in life. Oh, whoops. To make your best. Let's see. So I think what they say when they say isosceles trapezoid, they're essentially saying that this side, you know, it's a trapezoid, so that's going to be equal to that. And they're saying that this side is equal to that side. It's isosceles trapezoid. Okay? Which of the following, and they say RP and TA are diagonals of it. So let me draw that. So let me actually write the whole trap. So this is T, R, A, P is a trapezoid. And let me draw the diagonals. RP is that diagonal. And TA is this diagonal right here. Okay. All right, let's see what we can do. Which of the following must be true? RP is perpendicular to TA. Well, I can already tell you that that's not going to be true, and you don't even have to prove it because you can even visualize. If you squeezed the top part down, right? Imagine some device where this is kind of the cross section. If you were to squeeze the top down, right? They didn't tell us how high. Then these angles, you can imagine that both of these angles. Let me see if I could draw it. That angle and that angle, which are opposite or vertical angles, which we know, that's the U.S. word for it. Those are going to get smaller and smaller if we squeeze it down, right? And in order for both of these to be perpendicular, those would have to be 90-degree angles, and we already can see that that's definitely not the case. All right. RP is parallel to TA. Well, that's clearly not the case. They intersect. All right, they're the diagonals. RP is congruent to TA. Well, now that looks pretty good to me, right? Because it's an isosceles trapezoid. You could if we drew a line of symmetry here, if we draw a line of symmetry, everything you see on this side is going to be kind of congruent to its mirror image on that side, right? So both of these lines, this is going to be equal to this, and I can make the argument, but basically we know that RP, since this is an isosceles trapezoid, you could imagine kind of continuing a triangle and making an isosceles triangle here. Then we would know that that angle is equal to that angle. Let's see, we could make see if that angle is equal to that angle, then, well, actually I'm not going to go down that path because I think that'll be, but you can almost look at it from inspection, although maybe I should do a little more rigorous definition of it. But RP is definitely going to be parallel, it's definitely going to be congruent to TA, right? Because both sides of these trapezoids are going to be symmetric. And so there's no way you could have RP being a different length than TA, right? Since this trapezoid is perfectly symmetric, since it's isosceles. And then D, RP bisects TA. RP bisects TA. And I think there again you can show that if you were to, let's say if I were to draw this trapezoid slightly differently, if it looks something like this. Let me draw it like this. If this was the trapezoid, and then this is also an isosceles trapezoid, and then the diagonals would look like this. Whoops. The diagonals would look like this. So here it's pretty clear that they're not bisecting each other, right? It's in order for them to bisect each other, this length would have to be equal to that length. And that's clear just by looking at it that that's not the case, right? That is not equal to that. So they're definitely not bisecting each other. So you can really, in this problem, knock out choices A, B, and D and say, oh, well, choice C looks pretty good. But you can actually deduce that by just saying, by using an argument of all of the angles, that this angle is going to be equal to, let me see if I can make the argument. Anyway, that's going to waste your time. But that's a good exercise for you, is to make the formal proof argument of why this is true. Although you can make a pretty good intuitive argument just based on the symmetry of the triangle itself. Anyway, see you in the next video.